I would like to introduce a little bit the format. So this is a format that we run once a month. It's called Touch Bases with Novel R&I projects working on bioplastics, because we're European bioplastics, and that's why we want to know a little bit more about what you are working upon. Now, today, we are working we're having a talk with Cristiano Varrone, but before I introduce Cristiano and the project that is representing and coordinating, just would like to tell you that this is an occasion for you to explore possibilities for collaborations, also for meeting potential partners for future projects, and also get some first-hand insights. This project is a bit young because it just started, so we're just at the beginning, but you can have a look at the plans and try to understand if there is something for you, that maybe you can follow it a little bit more closely in the future. So this kind of event is running once a month, online, 45 minutes, around 20 minutes for a talk, 20 minutes for a Q&A, 5 minutes it's for me for introducing the format. So this is a very nice way for you to connect, especially during the Q&A with the coordinator, but also with other people who might be in the call. If you are interested in presenting your own project, mature one, just started one, get in touch with me or with Estela, my colleague. This is our email address. I will put everything then in the chat, so don't worry about taking now notes. And just get in contact with us. Calendar. We got many events that are coming up quite soon. We have one on the 24th of February with EOILE. That's also a project funded under the same call with Maria Jose Juarez, which is working for Geiker, and she's looking at oily products and packaging for oily products. 24th of March, we are looking into the project BioSupac that is led by IMPLUS. This is a more mature project, so we will talk about the demonstrators of this project and what actually they can bring to commercialization, but they might be looking for some partnerships. So if you are into PHA bias-based rigid packaging solutions, but also production of PHB from brewer spent grains, this is the talk for you. 21st of April, we changed the topic. We go into in-soil applications, and we will present the SOUL project, which is led by ITIP. And we will have a look at this kind of applications that they're planning to have. This is also a very young project. If you would like to register, all the different events are listed on Eventbrite, so you can just go to this page and have a look. And this will help you out in following up the talks. Now, it's my pleasure to have today here a connational, Cristiano Varrone, but also in a different location than Italy. So he ended up in Aalborg, very north. He's the coordinator of UPCYCLE, and UPCYCLE is one of the projects that has been funded under one specific call. Cristiano will tell you about this. He's focusing on sustainable plastic biorefinery for recyclable and biodegradable packaging. So topic is packaging, but from the biorefinery approach as well. And I will just now put you in the spotlight, Cristiano, so that everybody can see you. Cristiano, you got the floor. Thank you for joining us today and for this time together.
Yes, thank you, Chiara. Thanks very much for the introduction and the invitation. Hello, good morning to everyone. It's a pleasure to have the opportunity to present the UPCYCLE project. And as Chiara already mentioned, I'm sitting in my everyday life in the northern part of Denmark, where I'm mainly working with fermentation and bioprocess technology. And the presentation today, let's see if here we go. Will be divided into the following steps. I will quickly start with an overall introduction of the project and describe a little bit the main idea behind UPCYCLE and the plastic biorefinery. And I will also show how this project is actually building up on the results of a previous Horizon 2020 project that finished last spring called Uplift. And I will show some examples of the technologies that we have been developing, some of the lessons learned and challenges, and then show how this is the starting point for the UPCYCLE project, where we will try to overcome some of these challenges and overcome the scalability issues. And I will show some examples of the conversion routes and the end user applications of the UPCYCLE project. All right, I will go to pointer. So what is UPCYCLE? So the main aim of UPCYCLE is to valorize and turn currently non-recyclable mixed plastic waste into highly recyclable and at least compostable packaging material. And the concept, you can see it here on the left side. We would like to start with these challenges. Mixed plastic waste that currently is difficult to recycle, and applying chemoenzymatic technologies to depolymerize, break down these plastics in a selective way into constituent monomers, and then follow up with a second step of where we do something called upcycling or bio-upcycling, where we use wholesale catalysis to convert some of these monomers into new building blocks. And together with the fermentation of second generation biomass, we will create some bio-based compounds that will be integrated together. Next step will be through eco-design, so design for increased recyclability, where we combine bio-based materials and the monomers coming from the mixed plastic waste into new eco-polymers. And then through formulations, we will focus on furan-based, PHA-based, and PLA-based packaging. The overall idea is then to scale up the best technology to TRL7 and do some end user testing. And here on the right side, you can see some of the applications. I will get back to this in a minute. Where do we start? What do we mean with plastic biorefinery? So our starting point was from the idea of, can we use post-consumer plastic waste as a feedstock for non-conventional biorefineries? And this was the starting point of this Horizon 20 project called Uplift that lasted from 2020 to 21 to 2025, and so we increased the technology from TRL3 to 5. And the main idea was basically to combine two feedstocks. So one was this plastic waste that we obtained from a Danish recycler, and this was the fraction that they're not able to sort, and they sent for incineration to Germany. And through different technologies, then combine this with bio-based fermented building blocks. So here we were basically focusing on 3 steps from a technological point of view: chemoenzymatic depolymerization of the plastic waste, and then wholesale, so fermentation and bio-upcycling of the hydrolysate, and also fermentation of bio-based building blocks into new polymers, into new building blocks that then are repolymerized through eco-design principles. Some of the examples from the chemoenzymatic depolymerization, here a scale up of up to from lab scale to 300 liters of enzymatic depolymerization of post-consumer PET waste using an engineered enzyme that is a cutinase. It's called LCC, and the specific mutant is called LCC-ICCG. And our idea was to focus on working on a robust process that could decrease the process costs. So by using only crude enzymes, so the new supernatant without enzyme purification. At Aalborg University, we have developed different strains that could express this enzyme and also accumulated in the supernatant. Then we have transferred this to German partners of Leipzig Institute HKI. They have done the optimization and tech transfer and then scaled up to a 300-liter reactor. And here on the right side, you could see this the 300-liter reactor that was basically loaded with cryomelt PET powder, and we were able to hydrolyze 25 kilos of this post-consumer PET waste, and this was then sent the hydrolysate and also the freeze-dried terephthalic acid was sent to a partner, in this case UCD, University College Dublin, for the upcycling into mid-chain length PHAs and PHOs, so focusing on the octanoate and PEF. And we also sent it to DTU, to the Polymer Center, to see if it was possible to recycle this terephthalic acid to rPET and also to new polymers that I will get back to in a minute. An example here about the fermentation and bio-upcycling. Here a production of 4-hydroxyphenyl acetate This was developed by Forschungszentrum Jülich, where they have engineered a Pseudomonas taiwanensis bacterium strain in redirecting its natural pathway to produce aromatic amino acids, and this was redirected in the production of this 4-hydroxyphenyl acetate, which we call HPA, that can be used as a aromatic building block. And here you can see that the strain was developed by Jülich, and then they have transferred it again to HKI for the optimization and tech transfer. And you can see how starting from relatively low concentrations of titers of product, it was possible to increase up to 10 grams per liter. And this was then scaled up at bio-based pilot plant. And here you can see several kilos of the purified product. What did we do then with this new bio-based aromatic building block? This was sent to partners at DTU and AIM+, and they worked on trying to make new polymers. Here a homopolymer, which we call, basically PHPA, so polyhydroxyphenyl acetate. And we tried out the different properties of this new polymer. We also produced new bio-based additives and then tried to make different combinations of the different products. A concrete example from one of our partners, the compounders Biomi in Croatia. They were testing twin extrusion and cast extrusion to make flexible films, and they tried different combinations of materials that we were upcycling, combining it with commercially available, in this case PLA, where they were combining it with our new aromatic polyhydroxyphenyl acetate, or with the bio-based additive, or with the mid-chain length PHAs. And they saw that depending on the formulation, they were having different properties of the flexible film. An example from AIM+, they also tried to see if it's possible to use smart formulations for bottle production. And here you can see an example with injection stretch blow molding, where they were blending, for instance, PLA, so commercial available PLA, with our upcycled mid-chain length PHA, which is called PHO in this case because it was mainly containing octanoate. And they saw basically that it was able to provide superior processability, reducing the resistance, for instance, in the flow, and that this could lead also to lower softening temperature, so leading also to potential savings in terms of energy. One clear challenge, which is maybe also typical for recycled content, is that we still had this coloration problems. On the left side, you see the commercial bottle based on commercial PLA, and on the right side, two examples of the uplift technology, so with the recycled and upcycled materials, and you could see clearly that this is not completely transparent. And a last example, another partner called Tecnado, which is based in Germany. They were responsible for flat sheet extrusion and were able to produce rigid packaging that had reasonably good mechanical properties, provided that a certain thickness was used. So overall, to sum up a little bit here, we saw that it was possible to produce many different flexible sheets and combine different of these building blocks, obtain different properties also, but it was very clear that we also had to compromise between the processability and the mechanical properties of these materials. Here you see different examples, but actually Tecnado and Biomi have done many, many more tests. Most of them were actually very difficult to process, and these were the best results obtained. So what we saw was that actually these new upcycled materials, they are providing quite interesting properties to the material, but the best strategy is to use them in low amounts, almost as additives to modulate the properties. And a good example was, for instance, this aromatic bio-based PHAs, hydroxyphenyl acetate, that is an aromatic compound, and incorporating that into an aliphatic commercial bioplastics for polyester, for instance, PHA or PLA, we're able to modulate the properties. So what were the lessons learned from Uplift for each technological step? I would say for the enzymatic depolymerization or chemoenzymatic processes, we could see that the processes work really nicely with amorphous materials and pure streams. But once we started to work with real post-consumer mixed PET waste, for instance, crystallinity became challenging and the depolymerization efficiency decreased significantly. Also developing new pathways from waste streams usually leads to low titers. You saw you maximized, improved the hydroxyphenyl acetate production to 10 grams per liter, but of course from an industrial perspective point of view, we will need to increase further to make this economically viable. Of course, when we scale up, we also found some challenges when operating, for instance, the 1,500 liter reactors at bio-based Euro pilot plant. We could see that the downstream processing protocol that was optimized in small scale was working really nice in the lab, but it had to be readapted and optimized further in the large scale because we in the first place, we had quite a bit of material loss. What we also saw was that the best choices from a bioprocess point of view, so the materials that provided the best properties in terms of titer, productivity, yields, is not necessarily the one that is the best processable then from a material point of view. Here, an example of this mid-chain length PHAs. It was possible to upcycle our plastic waste into these PHAs, which is really nice from a bioprocess point of view, but this material is quite sticky and it's really difficult to process in the extrusion machines then, and needed some additional steps to make it actually really processable. And then last but not least, of course, economic viability is still a major bottleneck. We know that already from bioplastics that are more expensive compared to the fossil-based equivalents, and recycled material is more expensive than the virgin equivalent. So this is of course still something we need to work on. And this is the starting point of the UPCYCLE project, basically. So in UPCYCLE, we started from the bottlenecks that we have identified in Uplift through techno-economical analysis and LCA. And we want to address these scalability issues. And here you can see the consortium, the 19 partners involved. In Uplift, we were 15 partners, so we invited 4 additional ones, mainly from the industrial side. And we also have an interesting industrial advisory board that joined. And so to give you an idea of the structure and of the solutions that we propose, just quickly description, we try to answer the call, which was called biodegradable polymers for sustainable packaging materials. And the main requirements were basically to develop technologies that could improve the industrial leadership of Europe, increase diversity of the internal supply chains, and improve also the EU resilience. More specific, the scope, what we were required to focus on at least 4 of these. So we were asked to develop, scale up, and novel advanced biodegradable polymers. So the focus here was on biodegradability of these polymers, as well as innovative processes. And probably the biggest challenge of all, to produce new materials that had an economy of scale comparable to PE, so polyethylene, polypropylene, and PET, but with improved sustainability profile. So here the idea is that we need to decrease the costs, of course, and make it more competitive with fossil fuels, at least fossil-based polyesters and polyolefins. This is a very big challenge. And sustainability, another target was also to produce more sustainable additives. This is a big challenge as well, because if we produce biodegradable plastics, we cannot keep using the same additives that maybe are not degradable or maybe could leak as toxic compounds in the environment. So we need to make sure that also the additives are more sustainable and biodegradable. And finally, develop processes that can be scaled up to large pilot level. So the main objectives, how we try to answer this call, was to scale up and demonstrate a versatile biorefinery process that we had developed in Uplift. In Uplift, we finished in a TRL around 5 to 6, and here we would like to bring it one notch up to TRL 7. And one of the strategies to improve the processes and decrease the economical costs is, of course, process intensification, and this is AI powered in different steps. So we will use machine learning, for instance, in improving our catalysts, and this is both biocatalysts, but also new and benign metal-based guanidine catalysts. We will also use AI and machine learning for the improvement of the new polymerization strategies, and also we will use digital twins for the optimization of the complete overall processes to maximize, to recover energy, material, and water from the different processes. We will focus on smart polymerization and formulations. So here the idea is to through eco-design principles again, to fine-tune the performance of the new materials that we want to develop. As mentioned, these will be PHA, PLA, and furan-based polymers that will be formulated for 4 specific user cases. You can see them here for both food packaging and cosmetics. And we will need to keep the safe and sustainable by design as a guideline, as a red thread that connects everything. And we will target a decrease of greenhouse gas emissions by 30%. And big challenge also here, improved economic viability by decreasing the minimum selling price by 40%. What is the structure and what is our approach and the main outcomes? This is a bit of a complex figure. I will walk you through the main concepts here. So the idea is that UPCYCLE is working on 2 blocks. On the right side here in green is the development and scale up of a of a circular plastic biorefinery, where we have different outcomes focusing on the technology, so the chemoenzymatic depolymerization, and then the bio-upcycling of both monomers and bio-based building blocks. And this needs to be scaled up and needs to be economically viable, and will provide then the material needed in the second block, which you can see on the left-hand side, the blue block here, which is smart formulations for new biodegradable ecopolymers. The idea is that we need to increase the TRL from TRL 4, 5 all the way to TRL 7 for the selected technologies, and the guiding principle here is that we will compare different technologies, and then through LCA and techno-economical analysis, we will decide which are the most promising ones for subsequent tech transfer and scale up. And then only 2 or 3 of the best technologies will be fully scaled up to TRL 7. As you can see in the center here, sustainable, safe and sustainable by design is in the middle of these 2 blocks, and this is because this is not only regarding the production of new chemicals and new polymers and the formulation of these, but this needs also to involve the processes, also the bioprocesses that need to follow the same principle. So avoiding toxical catalysts, substituting them with more benign alternatives, and the same with chemicals, reduction of energy consumption, of water consumption, and so on. All right. So this to conclude, so give you a bit more concrete example of our conversion routes and our application. So the idea is we start here in the left side with different types of plastics. We have different polyesters and different kinds of both fossil-based and bio-based, and also polyolefins, which we can find in a mixed plastic waste. And then you can see that through different technologies, we will depolymerize this material. In the case of polyesters, PET and PBAT, for instance, we will use cutinases, so enzyme technology for depolymerization. In the case of PLA, we have this guanidine metal catalysts from our partners from Aachen University. And in the case of inert polymers, we will basically combine this with chemical recycling, so with pyrolysis of the polyolefins, and then we will bio-upcycle the obtained pyrolysis wax. So we will have different processes for the different streams. For instance, terephthalic acid can be upcycled into either mid-chain length PHAs or PEF, for instance. The monomers from the PBAT can be used, for instance, through biocatalysis to produce new bio-based plasticizers, and so on. And then you can see that we will create different formulations. And the main applications here will be for the dairy industry, where we will try to produce several hundred kilos of packaging material. This will be sent to our partners in Spain, Eroski, that will try the properties of these new formulations in terms of sealing capacity, vacuum conditions, so holding in vacuum conditions and low temperatures. We'll work with vegetable flexible packaging. Here we will test shelf life for several months and monitoring the properties such as gas and vapor transmission. Eroski will also test different beverage bottles, and our partner in Turkey, Aviap, will also test best properties for personal care packaging. Idea then is that these new materials need to be either biochemically or organically recyclable. All right. To conclude, I would like to extend an invitation for collaboration, or mention a couple of collaboration opportunities. One is we are still looking also to expand our industrial advisory board. We already have some interesting partners, BASF, Carbios, and Arkema, but there might be other partners that could be interested in this technology, and we'll be very happy, of course, to have the industrial perspective on board, so that we can align our strategies in the right direction, that it is relevant for the industry as well. End user applications are very relevant. We have identified some, but there might be others that could boost the implementation and increase the capacity of bio-based and biodegradable materials in the market. We're always open for, of course, scientific collaborations. We are 5 sister projects, but there might be others we're not aware of, and scientific collaborations are always very beneficial to reach critical mass. This includes also, we were talking at the beginning, standardization, which is relevant, science to policy, where we can have a higher impact, and of course, last but not least, also just networking and clustering events. With this, I would like to thank you all for your attention, and all the partners, which you can see here, for a very nice start. As Chiara mentioned, we just, we're still at the beginning of the upcycle, but the consortium has already worked together in the previous project. So we are already collaborating very strongly, and we'll be, of course, happy also to extend to collaboration to other projects as well. And with that, thank you, and that's it from my side.